Stewart here. Today we're going to talk about asymmetric cryptography with Microsoft's built-in libraries and BouncyCastle. You can find the source code for the demos I'm doing today out on my GitHub site, and you can use my Asymmetric Crypto helper library by pulling it in from NuGet.org. Let's start by using the Microsoft built-in library, which is in the namespace of system.security.cryptography. So what we're going to do for the purpose of these tests is when we first set up the test, we're going to make an RSA object, call RSA create, and that's going to generate a random key with the default values. And because it's an RSA key, it's going to generate a public key and a private key. And the RSA object will then expose two methods, export RSA private key and export RSA public. For the purposes of the testing and for just using RSA in general, remember that a public key can only be used to encrypt things. And you could publish that key on the side of a bus and it would be perfectly fine, because all anyone can do with it is encrypt things that they intend to send for you to decrypt. Couple of tricky things there though. One is, you really don't want to store these things in files or put them somewhere they could be lost easily. So whether you're doing symmetric encryption or asymmetric encryption, as we're demonstrating today with RSA, you want a safe place to manage your secret. And so you want to use something like Azure Key Vault, HashiCorp Vault, which we have a demo on as a separate video, or CipherTrust Key Manager. Basically what you want to do is generate keys and put them into your key management subsystem directly so that they don't hang around. And every time you need them, you need to go and auth to that subsystem and say, look, I am me and I need to encrypt something, so give me the public key. Or I need to decrypt something, give me the private key. And that's kind of okay, but it's even better if you never ever get to see the public key or private key ever. And how do you do that? Well, you say, I have this bag of bits, this byte array, and I'd like you to encrypt it. And I'd like you to encrypt it using my stored key pair that's called XYZ. And I have this bag of bits that's been encrypted with XYZ. I'd like you to decrypt it and give me back the decrypted bits. That keeps the keys from wandering around outside of your encryption and security management infrastructure. So for simplicity in this demo, I'm not using a key manager. Maybe that's a good future video. If you're interested, let me know in the comments. And instead, I'm generating keys in memory, or I'm generating keys on the file system and sucking them up and using them in the unit test to show you how to use the cryptography libraries to do useful work. But it's not a best practice. In fact, it's kind of the opposite of that. My intention isn't to show you the best practice for key management in this video. My intention is to show you the power of asymmetric cryptography to protect things. And particularly, there are some useful scenarios for using asymmetric cryptography. Again, the most common is, I want to give somebody a key, anybody a key, that they can use to encrypt things and send them to me, but only I have the private keys, so only I can decrypt them. There are lots of business scenarios for that, right? Whether it's sending confidential emails, and there are several email protocols that work with asymmetric cryptography, including SMIME. There are secure FTP protocols that you can use to send FTPs back and forth. FTP all by itself is a protocol, just ships the plain text, but you can use SFTP to have a higher level of protection. And if you really want a high level of protection, you want to double encrypt. So you want to use a wire protocol that's secure, HTTPS, SFTP, AMP with encryption, whatever. But you also want to then encrypt the payload. So even if somebody snoops the wire, they can't get at your secret stuff. Without the decryption key, it's no good to them. or at least you've gone one more step in thwarting them. Nothing is ever truly safe for a couple of reasons. First, encryption is based on essentially math problems that are so hard that in computing the solution, it would take longer to compute the answer than it would the lifetime, the intended lifetime of whatever the secret is. And second, at some point, you have to have some keys, and they have to be somewhere, and that somewhere has to be managed by people, and people are always the vulnerability. So there is no absolute perfect key protection. You can use better algorithms or worse algorithms. And by the way, before you pick an algorithm, you should definitely check to make sure that your algorithm hasn't been compromised. For example, a popular algorithm for asymmetric cryptography is called DSA. And for a while, there was a compromise to that algorithm. In other words, what does a compromise mean? A compromise means that I can look at the ciphertext, and there's an exploit that lets me get the plain text for that ciphertext. That's what vulnerability in cryptography means. Other kinds of vulnerabilities are I'm snooping on the plain text before it's enciphered, so I steal it before it ever gets encrypted. Or I steal it after it's been decrypted on the other end. So you've got to think through all of those things and just make your systems as hard as possible to be compromised. So let's look at some code. Again, for the purposes of this demo, we're just going to focus on how you can make RSA keys, and I picked RSA because that is the original algorithm, and it's still a really good one. As the algorithms underneath what's called the cipher, underneath RSA, which is mostly a protocol of defining what RSA looks like, you get extensions that have been added and better cryptography and more bittedness. So the bigger and more complicated your keys are, the harder they are to solve the math problem to get you back to plain text. Let's try the Microsoft way. And again, this is not a knock on Microsoft. They needed to provide basic RSA cryptography that supported things done on the Windows operating system. It's got pretty reasonable RSA bittedness, and the default behavior uses a reasonably strong algorithm out of the box with very little ceremony or fuss from you, as we'll soon demonstrate. Here in my test setup, I'm going to create an RSA object, and this RSA object is from system.security.cryptography RSA. When I create this, it's going to generate an RSA object that has a public key and a private key, and when I call export RSA private key, I get a byte array with all the private keys in it. And I could then write those private keys to a file, or write those private keys, even better yet, to my key management system, and they could be used to encrypt and decrypt things going forward. In this case, I don't really need the public key. So using it is dead simple. Here in simple test, what we'd have is I just made a short little string, and I said, okay, I want to use the helper wrapper I wrote around Microsoft RSA called AsymmetricCrypto Client Native, and I pass it in the private key bytes, and then I have two simple methods, encrypt and decrypt, that encrypt and decrypt the text, and I make sure that they came out the same. By the way, anytime you implement cryptography, you ought to implement a test that encrypts and then decrypts and then compares the results to make sure they're the same. Basic cryptography. This is not really very hard. And there's not a whole lot of code in my little helper, but you can go look at it up on GitHub. The point being is that the Microsoft solution allows you to get to asymmetric cryptography that's pretty okay, really quick. And it works okay. And it's relatively fast in execution. But it's not tremendously compatible across platforms, and it doesn't support all of the modern algorithms that are used to do cryptography. It doesn't support a lot of bittedness. It has restrictions on how big the ciphertext can be, which are the result of how big the plain text can be. It's got a lot of trade-offs. So it's really simple, but it's not as sophisticated as something else. So there's a group of fine people who came up with better cryptography. And The better cryptography is called PGP or GPG. PGP was the Open PGP protocol, is the protocol that's supported across all operating systems. The GPG is a wrapper around that. Here is my favorite GPG utility, although I have 3 or 4 different crypto suites on my computer for doing different kinds of things. You'll find this one the easiest to use. And it allows you the full range of things supported by OpenPGP, including some quite complicated scenarios. And you can use it to do all sorts of encryption and decryption and getting hashes for things. So you can take the hash of a file, for example, and in the download page, you can say, hey, if you download this and you do check hash and it doesn't come out to this hash, this thing's been tampered with. It's evil. Don't use it. This is the full boat suite of things that you can use from the command line. And it's got a nice Windows GUI called Cleopatra. It's got pretty good comparable support between Windows and Linux and Mac and the other operating systems. As long as they support OpenPGP, the chances are if you pick algorithms that are supported across the platforms you intend to use, including the phone. But if you pick the right algorithms, and you can go look on their manual pages and see what's available, and you pick the absolute strongest combination that you can imagine, you can then generate public keys and private keys. By the way, it also lets you generate symmetric keys and hashes and all sorts of marvelous things, and you can go and read about that here. On the other side of the equation, if you're writing code in C#, which are my examples are written in, you probably want to use a library that supports the full gamut of PGP things. And that library's name is BouncyCastle. Here is the BouncyCastle website, which is the Legion of BouncyCastle. And the BouncyCastle folks wrote libraries for C# and Java that support the OpenPGP experience and allow you to do many good things. Here's the thing with BouncyCastle though. BouncyCastle has a steep learning curve if you are not already pretty versed in crypto. So while BouncyCastle is super powerful and allows you to just manage things down to the finest level of granularity, it can be a tough uphill sled for people who just need to do some cryptography. And so Matasaurus wrote PgpCore for C#, and it makes using BouncyCastle for basic scenarios a ton easier. And this is the GitHub page, and there's a new Git package, as you'll see when we go show you some code. And it significantly makes doing routine things that you're probably going to want to do on a regular basis a ton easier. So for me, when I need to do PGP compatible encryption and decryption across, or hashing across a wide variety of platforms, I use, OpenPGP, so I have compatibility, and I use BouncyCastle, but I use it facaded by PgpCore to make my life easier. And to make your life easier, I facaded PgpCore for one specific scenario, and that's encryption and decryption with RSA. Okay, let's get back to some code. I want to make myself a pair of PGP public and private key. And I'm going to do that by using the PGP command line. But for the purpose of testing, if you just use PGP or GPG's command line, what happens is the keys that you generate go into your operating system key store. And while that may be desirable in some circumstances, if we're just trying to test things, right, if we're developers and we're going to be creating and destroying keys, and we don't want them to fill up our, machine key store, every operating system has a key store, we want to sort of get a workaround that allows it to skip using the local key store. And in GPG parlance, this is called an ephemeral home directory. So this is a PowerShell that makes a pretty good RSA key pair using the ELGE curve and a bitedness of 1024. I could use a higher bitedness than that, but 1024 is not bad. 2048 would be better. Obviously, these are going to be powers of 2. And I'm going to set a password. Parenthetically, your password should live in your key management system. In a perfect universe, your key management system should generate the password, which you should never see. Again, you want things to happen over there away from as many humans as possible. But for the purposes of being able to do this on your local machine, you need to have a password. And so I'm hard coding a password into the demo. Don't do this in real life. Okay, I'm going to set up my ephemeral home directory. You can go read the PGP man pages for why and how to do that. I'm going to generate a password file, and I'm going to get rid of the config.txt file I'm going to use to generate my PGP key pair. If I have an existing PGP key pair, I'm going to get rid of those. Here is the secret sauce behind batch generating keys. That is, generating keys from the command line without any human input. Why is that important? Because you're probably going to want to generate your keys over there in a pipeline or in a managed job or whatever. And so we want to be able to generate these things without any human intervention. And normally, if you had a script like this, you would also have part of the script that would then entrust these things to your KMS, to your key management system, or your EKMS, which stands for Enterprise Key Management System. So your script will go, hey, generate me a random password, and I'm going to call this batch of secrets XYZ 47B/N, or whatever you want to call it, right? Have a naming convention. And then you say, well, store that as the password. Then I'm going to generate a public and private key, and I'm going to ask you to store those two, and then you can then go away and use them as we've spoken about. This turned out to be surprisingly hard to reverse engineer, and it took me a while to get, so I was producing valid PGP key files. There are validators online. Just make sure that if you use an online validator, that you never ever use those keys that you validated for any actual crypto. The validators are there to check that the keys that you generated are actually good keys, and they're valid and they have the properties that you think they have. And once you've got that up and going, then you should never use those again unless you make some more code changes. So we're going to generate a file that says this is going to define what what all of my key properties are, including what kind of key it is, how many bits it has. Depending on the kind of keys I'm making, you can supply key curve and a bunch of other things. I'm going to give it a name. I'm going to give it a password. I'm going to, and then at the very bottom of my file, I do %commit, which is PGP for, okay, generate it now. So you can see that at line 94, I call GPG in batch mode, and I say generate the key and use this key definition file and generate me a key. Where is that key going to go? Well, it's not going to go to standard out. It's not going to go to a file where you can get your gloms on it. It's going to write it to wherever the key store on your machine is. But that's inconvenient for the purposes of testing. So what we did was we told GPG that our key store was actually our temporary key store that lives on the file system for the purposes of testing. So after that command runs, and you go look in the ephemeral key store, there will be some files in there that represent the generated secret. And then from there, I can export my public key and my private key. And I'm going to specify what's considered to be the best practice for asymmetric keys, which is to add something called armor to them, which makes them just that much tougher. But it also puts metadata on the keys that is going to join the plain text as part of the ciphertext, so that when the decryption engine gets to it, it knows there's certain behaviors. So adding armor automatically signs and causes verification and things like that. So I'm going to do a bad thing here, and I am going to create a public key file, which actually isn't that bad a thing, right? I remember I said you can put the public key on the side of a bus, and it's perfectly great. But what I probably shouldn't do is generate the private key to a file. I should generate the private key to a stream, and I should have that stream write directly to my enterprise key management. But again, for the purposes of testing, I'm going to have it write to a file. And then I'm going to clean up my ephemeral directory so the binary things are gone forever. And the output of this is I'm going to get two files, a public key file that looks like this. And again, you can give this to anybody. It's perfectly safe. And I'm going to get a private key file, which no one should see, including you, usually, that looks like that. They're just big blocks of complicated crypto text. Now that we have a public and private key file, our test, which hard codes the passphrase, again, don't do this in real life. You should go get passphrase from your enterprise key management store and put it into a secure string and not a string. And we can go read the public PGP text and the private PGP text off of disk. Parenthetically, in many cases, you'd see public.asc and public and private.asc. The ASC means that it is in ASCII armor format, e.g. the file format that I just showed you. In this case, I generated the text files just because it was easier to do. So now I have a private key and a public key and a password in memory, and I can do some simple encryption. Whew, that was something of a ride, wasn't it? So here we go. Using my little crypto helper library, which wraps BouncyCastle, which is wrapped in the other library. I have a constructor that takes public key, private key, and passphrase, which we've sucked into memory. And I do the test that you should always do, which is I encrypt some text and decrypt some text and assert that they are equal. What I've tried to do is make using the PGP keys in using, RSA, DSA, or whatever, but my test is for RSA, is easy to use as using the Microsoft ones, except that the PGP ones, which BouncyCastle understands, which we wrap in PgpCore so that we don't have to know a whole lot of detailed innards of cryptography. We can just get a nice helper. I've tried to make it so that for you, the mere mortal just trying to encrypt and decrypt things, is essentially very easy to use. And that's what there is to say about that. Hope that helps. Post any questions or comments or suggestions you have on the video's feed, and I will see you in the next video. Thank you for your kind attention, and if you like this content and want more, please like and subscribe to help support the channel.